So we're back to using this original example about the fair dice and event A being a prime number and B being a square number and C being an even number. And this time we're looking at independent events. So we want to show that B and C are independent. So we know that for two events to be independent, then if we take the probability of event B and we multiply it to the probability of event C, then we should get the probability of B intersection C if they are independent events. Now we can use this if with a couple of ifs on it because it's if and only if they are independent. So let's have a look. The probability of event B occurring. Event B was a square number, so we know that there are two square numbers on the dice, the 1 and the 4. Event C was if we got an even number, so we know that that's a half. So if we multiply these two events together, so 1/3 times 1/2, then we get 1/6. So this is the probability of B times the probability of C equals 1/6. Now if we also look at the probability of B intersection C, this is where both conditions are met for each of the events. So event B is getting a square number, so that's 1 and 4, and event C is an even number, so that basically equates to the probability of getting a 4. If we get a 4, it's an even number, and if we get a 4, it's part of event B, which is a square number. That's the only one that does it, which is 1/6. And so we can say, therefore, as probability of B times the probability of C equals probability of B intersection C, events B and C are independent. So always we come back for a mathematical statement to using that formula where we know that they can multiply together, and that gives us an independent, our definition of independent events. In the second part of the question, it says, are events A and C independent? So event A is getting a prime number and event C is getting an even number. So just so that we can see that, we'll write that out again. So event A is getting a prime number. So we know of the numbers 1, 2, 3, 4, 5, and 6. We know 2, 3, and 5 will fit that prime number condition, which means that there's a half chance 3 out of 6 of the numbers on the dice will be prime numbers. Now to get an even number, we know that we are looking at the probability of 2, 4, and 6. So again, 3 out of 6, or 1/2 of the numbers on the dice will be even numbers. Now if we're looking at their intersection, because we know we're going to be using a version of this formula again to show independence, the probability of A intersection C means that we're talking about a number that is both prime and even, and we can look through our list here of each of those events and we can see that this means we're talking about the probability of getting a 2, because it's the only number that satisfies the conditions for both events. So that will be 1/6. Now, if we were to multiply the probability of A times the probability of C, that would be a half times a half, which would equal a quarter. And so we can see that the quarter is not the same as the intersection of 1/6. So we're saying probability of A times the probability of C does not equal the probability of A intersection C. Therefore, events A and C are not independent. So now we've shown that they're not independent, and we've got some working and reasoning to back that up, and it's all based on this formula again, that the multiplying the two individual event probabilities together should give the probability of the intersection if they are independent events.